Okay, may I start?
Yes, sir, you can start.
Okay, thank you very much. Okay, thanks again for the presentation. Thank you very much. So this is the title of my talk. So this is me. My name is Roberto Caldelli. Thank you again for the presentation. So this talk is about basically multimedia forensics and in particular deepfake. And this is a brief outline of my presentation. First of all, I will introduce some security issues and will talk about the concept of the disinformation. And then I will do a step back in time, let's say, and I will show you how image and videos are being manipulated and from time to time. And then I will go through multimedia forensic discipline. In particular, I will show you which are the, let's say, the main approach, main techniques and the application. And then I will go through the, let's say, the new era of artificial intelligence and deepfakes, and I will show you which are the different kind of deepfakes, some characteristics, which is the basic definition of deepfakes, different kinds of image and video that are related to deepfakes, and then I will try again to give you some information regarding detecting how we can deal with these kinds of manipulation. And finally, I will go in detail on some, a couple, 2 or 3, depends if I have time to show this, of my research on deepfakes, and I will introduce some specific procedure, and then I will conclude. So let's start with security issues and disinformation. So images and videos have always been used to convey a message, to convey an information, and in a very direct and immediate immediate way. And this sentence that you can find on the internet is quite well known. An image is worth 1,000 words. I think it represents very well what is an image. So without using text, we are able to provide a very compact, very direct information. So if we look to this image, the message is that there is a cute fox that's brown with ears and so on and so on. But according to the presence or to the absence of the subject or of an object, or if there are some manipulation, the perception of an image is completely different. And in this case, I think that this is different. The fox is not so cute for the rabbit, or maybe is a hare here. So this is just a funny example to understand that changing the context, adding something or modifying something in the image, the perception that the user can have of the scene is completely different. And this can be used, images and videos and also audios can be used for different purposes, and in particular can be used when manipulated or when counterfeited for disinformation. And in particular, I would like to first of all distinguish between misinformation and disinformation, that usually are confused together, but there is a crucial difference between the two. And misinformation means that a content that is false or inaccurate or misleading is spread, is distributed without the explicit intention to someone, to deceive people. And in disinformation, instead, the content, the information is false, and it is distributed, is spread with the specific intention to gain an advantage or to deceive people. So this is very crucial. So in the first case, there is not the intention, and in the other case, there is the intention to deceive people. So this is a very important distinction. And according to this, we can see that disinformation is perpetrated each day, let's say, we can see each day by using images and videos. Here there are some just examples or or images that have been generated by resorting to AI or by manipulating some images that have been manipulated or regenerated by using technique like deep learning and so on. And so you can find this on social network and on the internet. So this is a very important problem. And the manipulation of images have a potential risk, different kinds of risk. In particular, they can this risk at a personal level, see, for per person. And in fact, this manipulated content can be used for bullying, for example, among teenagers or social network, for intimidation or for defamation of person. Can be used at financial level, for example, for extortion, for fraud, or to damage the reputation or of a person, or for example, of a brand or a company, and so on. And can be used also at societal level. For example, manipulating the news and the media, eroding the trust of persons, to damage the economic stability or the democracy, or can be used for the information warfare. And we have an example right now in our society, or can be used to manipulate the political elections. So the use of images and videos and also audios it's very, very crucial because there are some potential risks behind this. And so it is important to have some tools, instruments to try to fight this content and to understand if the content we are looking at is real or is fake or has been manipulated, where this content comes from, and so on and so on. So this is basically the theme, the topic of my talk is this. So let's take a step back through time, and we start to see how images and videos, in particular images and photographs, are being used in the previous year. Let's see. So here we can see that images and later also video, but in particular here photographs, have always been used and altered to modify the information that was conveyed to the viewer, in order to influence the way of thinking of the people. And here you can see that are a very important leaders that use images to modify this to provide a different message. And this is important that you can. This has been done in the analog domain, so that it was quite difficult, but has been done in this epoch. So you can see this different political leader like Stalin or Hitler or Mussolini in Italy. And so this is important to understand that the idea to manipulate the images in order to obtain an advantage has been always used in different period. Coming to the digital era, and here there are some just example of the first modification that we had at that time. For example, we had here there are different, obviously manipulation are different. Here there are only some example to categorize this kind of modification. First of all, we had retouching that was performed by using, let's say, filter, like in a well-known tool like Photoshop, for example. Or here there are other kinds of processing, like, for example, copy, move, or cloning. In this case, there is a portion of the image that is copied and then pasted to obtain a different meaning on the image, for example, to duplicate something or to delete something. And another kinds of modification was splicing, where two different images are put together in order to obtain a new image with a different meaning. And these are basically the three main cases of manipulation that we had. And other kinds of manipulation were in the domain of videos. And in this case, there was the idea to, or not only to modify the frame, but in particular to modify let's say the stream, the sequence, the temporal sequence of this frame in order to have, for example, different movements, different motion, different trajectories also depicted here. With, for example, by interpolating frame or by deleting or inserting different different frames. Can you hear me? Is it okay?
Yes, sir. You are audible, sir.
Can I go on? Can you
Yes,
give
sir.
me a feedback, please?
Yes, sir. Yes, sir. You are audible, sir.
Because it seems that you can hear. May I go on? Hello?
Participants can write in the chat box only, sir.
Sir, you are audible.
It's okay?
Yes, sir. We can listen you, sir. You can proceed further,
Okay.
sir.
Okay, I can go on? Okay. Okay. So these were the problems that we have. And so let's go on the other side of the barricade, let's say, by understanding what is multimedia forensics and which are the techniques that can be used to detect this kind of manipulations. And so what is multimedia forensics? Multimedia forensics is basically a discipline that it raised up more or less at the beginning of 2000s. And the idea was to use to develop an instrument for Hello, can you hear me?
Yes, sir. We can hear you, sir.
Okay. So there was an interruption, I suppose.
Yes, sir. For 30 seconds only, sir.
Unfortunately, okay. So can you tell me where, if I can restart from here or?
Yes, sir. You were in this space, sir.
Yes, can you tell me if it's okay if I go through from this? Can you see the slide?
Yes, sir. We can see your slide, sir.
Okay, so I can go on from here.
Yes, sir. From this page onwards, you can start, sir.
Okay, so thanks a lot. Sorry for that. There was no connection. It seems. I suppose it's okay. Okay. So let's start it again from this. So multimedia forensics, it's basically a discipline that it raised up at the beginning of 2000, and the idea is to develop techniques to make an assessment on multimedia content, on images, on video, in particular on the authenticity of this kind of data. What is important is that these techniques are based on a passive approach. So what does it mean, passive? Passive in this case means that these techniques can only use the content, take the content as input, an image, for example, to make an assessment. So differently from other techniques that are used in security, like digital watermarking, that you have the content at the disposal before the distribution can embed a watermark in it. This kind of techniques can only work in a passive way. So I think this is understandable. And the basic requests that were important are now important are to determine to identify the source of the origin of the specific content. So to try to understand where a content comes from. And the second question is it's about integrity verification, in particular to understand if a content has been tampered with, or also try to understand where it was the modification, so try to localize the tampering. Okay. So which is the idea behind this? Which is the idea to perform perform manipulation detection in this case? The idea is that there are some traces, some inherent traces that are a sort of digital fingerprints that are left in an image or in a video, in a digital media in general, during the different phases of the generation and processing of the content, in particular during the acquisition. So when an image is generated, there are some traces. I will go through this in a while. And there are traces that are due to the successive post-processing, for example, during the life of the content, or compression, uploading and downloading of the content on the social media. So there are some traces within the content. And the multimedia forensic techniques try to exploit this to understand, to make an assessment on this content. Okay, so this is the idea that there is behind. And I will try to give you some example, some ideas of which are the traces that can be used, like different clues to make an assessment on this. And we can divide it basically in two kinds of category. Basically, let's say the clues that are related to the acquisition, and the clues that are related to the post-processing. And here there are, for example, for the acquisition, there are some different kinds of traces like PRNU, color filter array, the aberration of the length, or for example, the different quantization table that I use, for example, for saving a file of the image in JPEG format for storage. And for example, in the case of post-processing, there are other clues that can be looked for, like double JPEG compression, or for example, filtering or sampling of an image, or for example, looking for some redundancies in the case of copy move, as I said before, or looking for inconsistencies, for example, in the illumination, the shadows, in the motion, in the case of a video. So these are just examples of traces. I will go through it just to give you, for 3-4 of this, just to give you an idea. One important trace that in multimedia forensic can be used is PRNU. Maybe you have been heard on this, and you have heard of this. It's PRNU means photo response non-uniformity. It's a noise. Basically, it's a noise, and this noise is generated in each content. In particular, you can think to an image during the acquisition phase, and This is due to a small manufacturing disuniformity that are present in the different CCD array. So this is due to the fact that when the same light hits a CCD cell, the response should be the same, but this is not the case. So this determines that there is a sort of noise, an invisible noise that is embedded in each acquisition, in each image, and also in video case. And this is also for different content. And these kinds of noise can be modeled as the equation here in the figure. And this is basically a sort of multiplicative noise that is embedded in the image. And this kind of noise can be extracted by using of high-pass filtering. And this can be used for two kinds of application. The first is basically to match an image to the acquisition device. So for the case of source identification, in this case, it's possible to determine that an image has been acquired from a specific device according to the presence of the specific PRU. Is a sort of fingerprint for the gun as a bullet. Okay, and this can also be used also for forgery detection. In fact, the absence and the presence or the absence of this PRU can be determined to understand if the content has been manipulated, or maybe the partial presence of the PRU can be understood like a sort of manipulation. So this is a very important trace that can be used in image and videos. Another important kind of trace is a color filter array. Color filter array is used in the acquisition to get a different color for each specific position of pixel, because in each position only one kind of primary colors is acquired, green, red, or blue, and with a different percentage, and the missing pixel are obtained by interpolation. So there are two kinds of traces in this case. The RGB pattern, which is a clue, so the distribution, the position of a red, green, and blue in the space, and also the absence of this color filter array can be used as a trace, as similar to PRNU. And also the interpolation, the fact that there is an interpolation to get the other position, and the algorithm used for the interpolation could be a clue itself that can be used in forensics. Another interesting clue can be used to determine the social network of origin or provenance. This means to try to understand if an image comes for example, from a specific social network like Facebook or Instagram, or comes from WhatsApp and so on. And to understand also if there has been multiple uploaded downloads on different social networks. In this case, the clue is determined by the fact that each specific social network applies distinctive kinds of combination of transformation that leave traces in the content. For example, the file name could be also a specific characteristic of a social network, as resizing used with different aspect corrections sometimes, or resample, or for example, the JPEG recompression with specific quantization table or specific quality factor. And also the fact that metadata can be changed, also in this case, can be used. All these different traces can be used to try to determine if an image, for example, comes from a specific social network, and so on and so forth. Okay, so this is another interesting kind of traces. These traces refers to the acquisition phase, so to the generation phase, to the origin. But in the case of post-processing, there are other kinds of traces that can be looked for. For example, one is important is a JPEG recompression. The fact that, for example, in the case of splicing, there are two images that are put together to generate a new image. In this case, to generate it with this new JPEG file, there are two effects. There is a desynchronization of the JPEG compression grid, and there is also a resampling to a new quality factor that determine a sort of periodicity, as exemplified here in the figure, of the DCT coefficient histogram. And so this can be, again, a clue to determine that there has been a JPEG compression that could be, for example, very useful to understand that there has been a photo montage. There is a composition of two images. Other traces are, for example, the presence of similar areas. Like, for example, it can happen when in a copy move attack, when a portion of the image is copied and cloned in another part, like here in the example to delete something. In this case, it's the traces that there are areas that can be described by using descriptor, like, for example, SIFT or SURF or other, that appear to be similar, to be, let's say, the same. And so in this case, it can be used to detect a copy move attack. And other kinds of traces concern the use of lights and shadows. For example, when images are composed, it's quite difficult to obtain the same illumination, because usually the source of lights is different in the images. And this can be seen in the shadows, or, for example, try to compute the direction of the illumination of the source by resorting, for example, to the subject, or by resorting also to the eyes. It can be models like spheres to determine which is the direction of the light. And if there is an inconsistency, as exemplified here in the figure on the right, between the different directions, is it possible that there is a manipulation? So these are just an idea of which are the traces that we can look for. We try to look for if we are lucky, and this, let's say, this works because it's possible to have a system. There are in literature procedures that are quite good to do this in terms of accuracy, very reduced false alarm or missing detections. But when you have to use this kind of instruments in the wild, in the real world scenario, you have to things are very are not so good, and so it's different because there are other kinds of processes that a content that an image, for example, has undergone, like common processing or the word adversarial processing. Common means that other kinds of processing can happen, like recompression for storage or for web purposes, or for social media sharing or laundering on the other network. For example, processor printing and scanning. These are common processes that can complicate the presence of some traces. And there are also adversarial attacks that are designed specifically to hide this kind of traces, to hide the manipulation, for example, removing PRNU, or to transplant PRNU between the image, or remove key points that are important for the identification, and stuff like this. So performance in this case are drastically reduced. So this is quite complicated. So this is just to have an idea what is, let's say, what is manipulation in images, basically, or also in video. And on the other side, what is multimedia forensics, and which is the approach, which is the idea to use traces, and how we can use this to determine and to make an assessment on the content. So let's go to the present time, to the AI era, and to deepfakes. And so let's try to understand how it's a situation, if there are some differences, and if there are something that is common, and there are both. So this is probably the first example, probably a I don't know. It should be the first example of deepfake. It's more or less around 2017, and you can see that at that time it was quite impressive, and you can see that the quality is not so good for now. And anyway, this is just let's say the first example of the application of deep learning, let's say to generate computer vision in general, I would say, to generate something that it was manipulated and fake. And so with the advent of the artificial intelligence, and in deep learning in particular, things have changed, and have changed in terms of manipulation, and consequently have changed in terms of multimedia forensics and detection, I would say. And in particular, with the deep learning, there are two important effects. The first is that deep learning is used to, let's say, to perform the same types of manipulation as before, but with a more realistic result, with a higher quality, and also with it is very easy, more easy than before to apply this kind of manipulation. So this is, I think, the first effect of the use of deep learning. The second effect is that there are not only the same type of manipulation as before, done better, I would say, but there are also different kinds of manipulation that are based specifically on deep learning, and in particular on the generation based on deep learning, that are known specifically with the name of deepfakes. So deepfake at the beginning was intended as the generation of video, manipulated video, like here on the right, where there was a real sequence, and that was modified, let's say, by changing the face, basically the face of the person. So the appearance was different. It seems that there was another person, for example, an actor, talking in the place of the politician, and so on and so forth. And then the use of artificial intelligence has determined a new different kind, let's say, of deepfake. So deepfake has become something more general, meaning something that is fake and is generated by resorting to deep learning and AI in general. And this fact is a generation of fully generated content, images and video, and also audio. I will not talk about audio in this talk, because I'm not so I do not research on audio, and just a little. Anyway, most of these things apply also to audio. So there is also the problem of the fully generated content. So this is quite different. So the situation is a bit different with respect to before. So there are also different kinds of manipulation. And let's go in detail on the concept of deepfake. So if we go in detail, there are different types of processing that are involved when we say deepfake. For example, according to the video sequence, there are different kinds of manipulation that can be treated differently, and they have different results. For example, there is a concept of face reenactment. In this case, there is a person speaking in the video, and the identity of the person, as exemplified here in the figure, is not changed, but only the expression, for example, the movement of the eye, the movement of the mouth, the cheeks, are modified in according to convey a different message, but the identity of the person is not changed. This is not the case of face swapping, where the face, so let's say the oval of the face is changed, is modified, and is overimposed on the face of another subject, and also on the body. So there is a change in the identity. And another important kind of processing is the lip syncing. In this case, the movement of the mouth are changed accordingly possibly to a different speech, to a different audio that could be malevolent, that could be different. And in this case, you have to modify the mouth and the lips in order to be coherent with the speech. So these are different kinds of processes that are involved in deepfake, when we say deepfake. And these are other kinds of processing that always indicate in the world of deepfake. For example, this is motion transfer. So in this case, there is just the transfer of the movement. It's a sort of a movement that is transferred to, let's say, to a sort of puppet with respect to an original video sequence. And in the case of images, there are other important kinds of, let's say, deepfake of processing that can be treated differently, that are the transfer of content. Here on the right, there is a zebra that is converted to a horse and vice versa. And also the style transfer. Style transfer is an important kind of processing that are which is in the world of deepfake. The style means, for example, here in a picture, winter is transplant in summer, and vice versa. So this is just to give you an idea of which are the transformation and modification that we can have when we talk about deepfake. And then there is another important aspect which is linked to the deepfake is the generation. So the synthetic generation can be obtained by resorting to different kinds of system, also commercial tools. There are everywhere. Here there are just example of tools that maybe you know, like Midjourney, DALL-E in a different version, and other kinds of tool. And these are able to generate synthetic content of very good quality, not always so good in. I will talk about this later. And this can be generated content by using, for example, just text to image. So just using a prompt to generate an image, or image to image. So they can generate an image or a video by resorting to an image as input. And the quality is very good. This is just an example, for example, of a generation of a synthetic video. They're generated by just a simple text prompt. Here, the application here is a HiGen. And the prompt is just simply generate a video with a man that speaks moving in a crowded street. And you can see that the quality is good. Anyway, there are some error here. You can see the car go back. So there are some small artifacts, but the quality is very, very, very good. This is just to understand how the life for forensics is becoming difficult. And another important, let's say, chapter is faces, the synthetic generation of faces, because this is important. As I said at the beginning of this talk, there are important security issues that are linked to deepfake, and so faces you can understand that are important because they deal with humans. And this is just an evolution of the quality of the generation of synthetic faces. In this case, you can see that through years the quality is improving. Here are other examples. Here, this is a very well-known case of Tom Cruise that has appeared on TikTok. This is a combination of a generation with also the use of an actor. And here, this is just another result. This is the quality of today, we can say. So you can see that the situation for images is improving a lot. And this is just an example of let's say a larger size. Here there is an image that is generated by, if I remember well, by using a generator of a referral network. And this is one, and the one is real. And I think we cannot distinguish these two images. I don't know if someone of the audience can identify if the left is real or the right is fake, or vice versa. And the quality is very, very good. And this is the answer. And so this is just to make you understand how is the situation at the moment with respect to what is deepfake, and which are the characteristics of deepfake, and what we intended to when we talk about deepfake. And I will tell you something very quickly, which are two of the basic methods to generate images, to generate deepfake in this case. One of the quite well-known methods that he used is the diffusion model. And diffusion model is a system that is based on two different phases, the forward one and the reverse one. During the forward phase, the system is trained to learn how to obtain a complete image, complete noisy image starting from an image. So in this case, the system learned to add slightly noise step by step till to arrive to a complete noisy image. And in the reverse phase, do the reverse. So there is a denoising process in order to reobtain the initial image by from the noisy image by subtracting step by step a small noise. And so it trains the system to do this. It allows the system in the reverse phase to generate an image, to be able to generate an image starting from a noise. And so this you can find on the internet different kinds of tools that are based on this kind of processing, different with different application, different structure. Another basic system for generate content in deepfake content, particular images, is based on GAN. GAN is means generative adversarial network that are basically structured as depicted here. There are two, let's say, systems, which are the generator and the discriminator, that are trained in an adversarial way in order, the first one, the generator, to create an image from random that it looks similar with respect to a real image. So in order to obtain a distribution of the generated image that is quite close, very close to the real image, in order to fool the discriminator that is here in the role to discriminate between the content, if this content is real or is fake. And so there are a loss for the discriminator and also a loss for the generator. So there is an adversarial training that has been done between these two, and the generator learns to provide very good content. The discriminator learns to distinguish better between the real and the fake image. So at the end of this process, we have a generator that is able to generate an image from an input that is basically noise. It can be used to generate deepfake images. So these two are basically they can be used then in different kinds of application. There are the two basic processes can be used to generate synthetic content. And these are some examples of the two. Here we have a real image and an image that is generated by using GAN, and an image that is generated by using a tool that is based on diffusion model. And the image are very high quality. You can see here on the left there is a real image. In the middle one is generated by using stable diffusion, which is based on diffusion model. And here there is another architecture, which is a style GAN that is quite well known to generate faces, that is based, as the name said, on GAN. And so you can see that the result is very, very good. So this is basically the situation on deepfakes. So as done before, let's try to go on the other side and try to understand how we can perform the detection of deepfake. And so in this case, we have more or less the same problem as before. We have to make an assessment on an image or on a video. And in particular, the question here is to try to understand if a content, an image, a video, or an audio has been synthetically generated or through AI or is real. And basically, there are two possible cases that are quite similar, but there are some differences. And there is a case in which the content is originally real, but the content is manipulated through the AI, for example, to add something, to add a face, like, for example, here in the example of Nicolas Cage. But the rest of the image, the background, the other object, and the other subject that are present in the image are not touched. But in this case, when we use AI to perform this kind of manipulation, for example, change the face, there are all the image is reconstructed, is regenerated. So if it's not so visible, but there are some small modification in the whole image, and if from a visible point of view there are no modification of the rest of the image, there are this very slightly changes in the image. And this is important from a detection point of view that can be used to perform deepfake detection. The other case is when the image is entirely generated, fully synthetic content, as I shown before. So in this case, when we have a fully synthetic image, so when an image is generated from noise, to perform detection, basically the idea is to try to look for the absence of something that is directly linked to the real world characteristics that is not present in the fully synthetic image. So this is the idea in this case. So the absence of elements that are typical of the acquisition, because a real image it should be an image that has been acquired from a camera of a smartphone. And so there is a processing behind this. For example, there is a presence of PRU, as I said before, or other kinds of processing that are not present or should have not present in a fully synthetic image, that maybe the artificial intelligence has not originated completely. So the absence or the partial absence of this characteristic can be used as a clue for detection. And other inconsistencies in this inconsistency I used, for example, in some inconsistencies in the light direction, in the reflection, that are typical of the acquisition phase. So the absence of this or inconsistency in this can be used again in this case to determine that the content is fully synthetic or is real. So we can say that also in this case, in the dealing with the fake, there are some traces that multimedia forensic techniques can look for. So there are some traces to find and to exploit to perform detection. Here there is an explanation of this. This is, let's say, an easy case. You can see that this image is being generated, if I remember well, by using Midjourney. And you can see that there are some inconsistencies, for example, in the writing here, on the writing of police here, or for example, in the hand, there are 6 fingers. And so in this case, it are some artifacts that are visible, so it's quite easy. But this is not always the case. So what we can do from a forensic point of view. So in this case, to deal with content that has been generated by artificial intelligence, by deep learning, we have to use deep learning again to fight this kind of manipulation. So this has been done time ago, initially by using, for example, machine learning based approach like Roberto machine, random forest, and so on, using different approach based on handcraft feature. So there is a destruction of particular feature, and used to train some, for example, a Roberto machine. And in the same way, we follow the same approach by trying to devise some forensic tools that are based on deep learning and that are driven by data. And so there are different architectures, as you can imagine, and also different data sets that has been built to perform training, to perform testing, and to obtain architecture that usually perform very well in particular cases, and but as I will show you later, that do not perform always well in terms of the application in a real-world scenario, for example. So also in this case, which are the traces? Again, we talk about traces and artifacts. So the traces are, there are some traces that are new. I will show you something in a while, but there are traces that are, let's say, old, that have been used in general in forensics. For example, like spatial inconsistency, for example, that artifacts that are visible in a frame or in an image, inconsistencies related to the environment, like, for example, incongruency between the subject in the foreground and the object in the background. And but there are also something that is different. For example, in particular, in the cases of synthetic generation, there are some clues that are related to the process of generation. For example, to the generation by using GAN model. And there are also other traces that are linked to the anomalies, for example, in the behavior of the person, on the physiological anomalies like high blinking or different, let's say, heart rate, when the heart rate is determined by looking at the color of the face, or the pink of the face and the cheeks in this case. So these kinds of anomalies can be used also to try to detect deepfake. And other kinds of traces like temporal inconsistency, like flickering, or also in the optical flow. I will show you something later if I have time. And other kinds of desynchronization, for example, in the audio or in the lips movement. So this is more or less our same traces as before, and as before in time, I mean. But there are also something new that are related to specifically to the case of deepfake. And so this is just an example of quite well-known techniques. This is a technique that was developed in 2018. It's quite well known because in this case, the deepfake detection in video sequence was determined by looking for the eye blinking, the absence, or the strange, let's say, high blinking of the sequence with respect to the real case. And another interesting application was by looking, for example, at the dynamics of the oral dynamics, so the movement at the end of the mouth and also of the ears. So inconsistency in this combination of two was a trace for deepfake detection. And this is another application that is another trace that is very, very interesting. This is this were for the video sequence. Okay, this is just for image deepfake detection, for image generation. And in this case, it's interesting to see that the process of generation leaves some clues in the frequency domain. Here there are represented the spectrum of the average spectrum of the images that are real on the left, and on the right, images that are generated, if I remember well, by a GAN process. And you can see that the spectrum is completely different. For example, the spectrum of the real is quite smooth, but in the case of generated images, there are some spikes that are periodical spikes. And so this is a clue that can be used, for example, to train a network, to train a classifier, to obtain a distinction between real and fake. And in addition to this, it's interesting to see that this can be used also to determine not only the fact that an image is real or fake, but also to make attribution. Attribution means that if you want to understand if an image that is fake, that is AI generated, comes from a specific generator. And you can see here the different kinds of generator, for example, stable diffusion, style GAN-T, big GAN, glide, have similar pattern, similar spectrum with these spikes, let's say, but the spikes are different distributed, have a different pattern, different organization. So this is a sort of fingerprint in the spectrum that it's interesting, that can be used to determine if an image is real or is fake, and if an image comes from a specific generator. And so, just to give you an idea on other kinds of traces can be used, I would like to give you just some hints on some paper of my research on deepfakes, and I will give you just a couple of ideas to understand what we can do in this case. And this is an approach that we have been working on it was around 2020, 2019 and 21, and it's the application of the use of optical flows to determine if a video sequence is deepfake or not. So in this case, it's about video deepfake, and the idea is to use the temporal domain of the sequence. The idea behind this was to use the optical flow. Optical flow is basically a motion vector field that can be computed among frames to determine the motion of the sequence. And the idea was to verify if the optical flow estimation was different for a real video sequence with respect to a deepfake one. And so we have seen that there are some modifications, light modification for example, in the distribution, or for example, in the values of this vector that can be exploited to detect the deepfake. These are just an example, very lucky example, I would say, that you can see that the vectors, for example, in the deepfake case, are a bit smoother with respect to the real one. And this kind of feature, this is a feature. This motion vector, this field can be used to train a network and to make a classification. So this is another example of the work of mine. This is on images, and this is on the problem of to detect, to distinguish between real image and image generated by diffusion model. And the idea is to obtain the work is on generalization, as I said before. The idea is to obtain a feature that it's able to generalize in order to perform quite well with different kinds of fakes, independently from the generator. So the idea is to try, in this case, to extract a feature that is represent, for example, the time of acquisition. Because surface frame in this case provide a description of the, let's say, of the surface that are present during the acquisition and are embedded in the pixel of the image during the acquisition. In this case, it is possible to obtain the extraction of the surface frame that are basically the description pixel by pixel of the tangent, bitangent, and cotangent. The normal, the tangent, and bitangent in each position, which refer to the different surfaces that are present in the image. And so the idea is that if an image is real, we have a sort of consistency of all this surface frame at the time of acquisition. And if an image has been generated, this consistency is not maintained, or is partially maintained, let's say. So this could be used as a clue to distinguish between real and generated. In this case, we have taken a specific component on this reference frame, and we have trained a classifier or different kinds of architecture has been studied to perform detection. And the results are quite good in terms of generalization. And a third example is just always in the case of distinguish between real and fake in the case of images. And the idea is always to obtain something that is able to generalize, so to work with respect to different kinds of the image generators. And in this case, the idea is to use this pipeline, and in particular to use a sparse autoencoder that is able to, let's say, to extend the description in a larger latent space. That in this case is 65,000 dimension in order to have a description in a larger space and try to understand, to select which are the features that are most important to represent what is fake, let's say. Because usually the feature that we are going to use, we use to train a model, they particularly refers to the specific manipulation. So what happens is that a model learned that specific manipulation is not able to generalize. So the idea of this work was to try to understand if there was a description that could be used to obtain which are the features that can specifically represent what is fake. And so this can be selected and used to train a classifier to make a decision. The idea was to obtain a compact, very compact vector of feature. In this case, this vector was just a 32 feature. So we are working on this to try to understand which is the right size to be used to obtain a consistent classification. And here there are some results. You can see that the system can work in dataset performance. So this means that the system is trained on some specific generator and test on all the others. In this case, on the diagonal, you have the case when the train and the train set and the data set are all the same generator. Not the training set and the test set are the same, obviously, but the generator are the same, so it works well. But if you go out of the diagonal, so in the cross dataset scenario, and you test a model that has been trained on a specific generator against all the other, you can see that the performance are quite good and the blocks are red or darker red. So this is a good start for to work on generalization. And this is an example with respect to other methods, the state of the art, and you can see that we achieve let's say a second best here in the state of the art with respect to the case of generalization. You can see here that there are different families, for example, content generated from GAN, from diffusion model, or commercial tools. This is just to give you an idea of how we can work, and so there is room for research. So let's conclude. Just some messages, some take-home messages, and something on open issues. So we have seen basically, which is let's say the situation on content, on image and video manipulation, in particular related with deepfakes. And we have seen the different kinds of techniques that we have, the different kinds of features that can be used, the traces that can be adopted. And in particular, there are different open issues to be tackled, obviously. And I would like to give you some ideas so maybe you can work on this if you are interested. And this basically are these two. The first open issue is generalization. As I said before, it's at the state of the art, this problem is still open. So the idea is that there are techniques, procedures that works very well when trained on a specific kinds of data, on a specific kind of generations. So the generation is known at the time of training, but when they have to work with respect to new kinds of content that's been generated by unknown unknown at the time of training, let's say the performance that usually are very, very good, in this case they decrease drastically. So this is the problem. It's not only a problem of, it's also a problem of data set, of data of there is a huge data shift between the training set and the test set, so the performance go down. But it's a problem of more of forgery. It's a problem of kind of manipulation. It's a problem of kind of generation that usually is learned in training, and that is not found during the test phase. So in this case, we have a problem. So generalization means this. And the other important aspect to finish is robustness. When we are developing techniques, procedures, architecture to detect deepfake, usually when we use these techniques on a data set in a lab case, I would say, they work very good. But when we use this in the wild, in the real world scenario, this is not the case. This is not the case anymore, because in the wild there are different. There is a huge number of manipulation of processing. They are completely different. That an image can undergo, a video can undergo, sorry, and so the modification that can happen can delete the traces that you are looking for, that we have seen during this talk, that there are different traces that we look. And so all these different transformation, a cascade of this different transformation can reduce or delete or invalidate these traces. And so in this case, the good performance that we had are not more there. And so this is another open issue that is crucial. So generalization, I think, is basic, and also try to increase robustness to use this kind of techniques in the wild, in a real world scenario. And so that's it for my side. Thank you very much for your attention. And if you have some question, I'm here. Thanks a lot.
Thank you, sir, for the informative session. We can now take the queries from the participants.
Participants can ask their questions directly to the speaker.
Sir, the first question they have posted in the chat box is, what if the AI generated image also takes care of light direction and surface reflections?
Sorry, I didn't understand. Can you tell me?
What if the AI generated image also takes care of light direction and surface reflections?
Yeah, if I understood well, which is the use of a reflection, you mean?
Yes,
yeah?
Sir. They are
okay.
Asking.
Yeah. It's very important. It's in fact the idea also, when I've been talking about surface frame, the idea is to use this as a feature to understand if there are some, let's say, inconsistencies in the reflection between the surface, between the object of the subject in foreground and the background, and if it's possible to find some feature or some instrument to exploit this aspect. This can be used for deepfake detection as an effective instrument to deepfake detection. And this is for example, this is the idea that I've shown before on surface spraying, for example. And if there are other tools, other instruments, other features that go in this direction, I think this is good.
Okay, thank you, sir. Another question is, how can optical flow and motion vectors be used to detect temporal anomalies in deepfake videos?
Yeah, the idea is to use optical flows is because when you have a modification in a video, and usually the modification by generating a deepfake, you have this modification generates some inconsistencies in the motion, in the variation, in the drift between the different frames, between the frames that are closer. And so the idea is that when you use artificial intelligence, this modification that generally in a real sequence are there is a good variability. There is a great large variability in this motion vector. In the case of artificial intelligence, in particular in the modification of a real video by using a AI technique, these fields are modified and let's say they become smoother. So because the idea is that there is something that is copy pasted this is not so correct anyway, just to give you an idea, copy pasted between the frames, so that this is not real anymore. And so if we are able through the optical flow or by using other kinds of techniques, other kinds of feature to evidence this inconsistency in the temporal domain, this is the case of a video sequence, that this is good for for video deepfake detection.
Okay, sir. Thank you so much for explaining very well the question. Any other query from any participant?
Okay.
One question is there. How do gradient descent and back propagation work in image-based models?
Sorry?
How do gradient descent and back propagation work in image-based models?
Do you mean in detection? You mean?
Yes, sir. I think that might be the query from some participant.
Because I cannot get to the question right. So you mean that the back propagation for deepfake detection?
Yes, sir. Yes.
I really don't know if we can use back propagation for deepfake detection, because to use back propagation you need to use the network. So generally in this case we have the content, and we have to develop a procedure and try to analyze the content that we have. So I think we cannot use for example, back propagation during the generation of a content. So we have not access to this. If you mean to use back propagation, for example, during the classification, for using, for example, an architecture that is based on deep learning, at the moment I don't remember if there is something similar in literature, and if I really get to the question.
Okay, sir. Another question is, how about opportunities of implementing deepfake in medical sector?
Very good question. Yes, this is an application. This is a sector that is very important. This is crucial, and there are in literature there are an important example of how images, for example, magnetic resonance or other kinds of analysis, can be modified by deepfake and can be used for malevolent application or other kinds of application. And This is very specific because in this case we have also different kinds of images that are different characteristics with respect to multimedia images as shown before. And so in this case there is room for to study different kinds of images, different kinds of modification. Anyway, this is very important. This is crucial. This is a basic application for security, the medical imaging sector. Absolutely, I agree with this question.
There is a last question I would like to ask. It is in chat box. Are autoencoders helpful in identify transfer and deepfake systems? Are
Yes,
autoencoder helpful in identifying transfer and deepfake systems?
yes, autoencoder have been using deepfake detection, and for example, in the case of that I've shown before, we use a sparse autoencoder, which is a bit different with respect to classical autoencoder. Anyway, there are different deepfake detection methods that are based on autoencoder. For example, there are methods that are based on, let's say, on variational autoencoder or similar that are used, for example, let's say for anomaly detection. For example, in this case, the model is trained, let's say, on real images, and the system is use autoencoder to learn to reconstruct images by using autoencoder. And the fact that when an image that is deepfake is given as input to this kind of detector, the reconstruction that we have in this case is different. It's a bit different, but it's usable to detect deepfake. So in this case, the system uses autoencoder to learn a sort of distribution, and auto distribution means that the sample is deepfake.
Sir, sorry to interrupt you. This is Dr. Sumati. Can we say that the GANs might be more efficient rather than autoencoders in deepfake detection?
I don't know. If we can see if
because during reconstruction of images with the implementation of autoencoder, we feel that GAN might be very efficient in constructing. That is why generator and discriminator are there, which could help to distinguish between the fake and real images.
Yeah, okay. Yeah, good. GAN are particularly good in generation, in particular in the generation of faces, as I shown here, and can be used in detection. And let me see here. This is GAN generated image. You can see here the quality. For example, here on the right is very good. For example, here GAN is better, in my view, to generate images that are with respect to a system that are based on diffusion model, because the image in the case of faces are more smooth, with color that are not so realistic, and so the use of GAN I think it's better. It's still better, but the quality is very good in each case. And use this kind of system for detection it's quite complex.
Thank you.
Okay.
Sir, this is Tuhin Shukla. I asked the question about the autoencoders. The question was, would autoencoders would be more helpful in identity transfer while implementing the deepfake? Like expression of another person and the identity of a person B. Would autoencoders would be more helpful in implementing it? That was the question, not in detection or implementing a deepfake.
Yeah. Autoencoder are used to for example to swap a face. Yeah. And also
So why are they more successful in doing that?
Yeah, you can use to do that. I cannot say what is better. I'm not how we can say that it's better. Anyway, the quality is very high in each case.
Thank you, sir. Thank
Okay,
you, sir.
you're welcome.
Any other query?
We can take
Thank
last
you, sir,
question.
for
Okay.
delivering.
Okay,
Thank you, sir, for delivering
thank you
a
very
highly
much.
informative and engaging session. Yes, sir.
Okay, thank you very
Sir,
much
your
for
session.
inviting. Thank you very much for inviting me.
Thank
Okay,
you, sir,
Thank
for
you,
the
sir.
session,
Thank
sir. It
you.
was very
thank you.
insightful session, sir. Thank you, sir.
Okay, thank you. Bye. Thank you. Bye.
Okay, sir.
Participants are requested, please fill the feedback form. It has been shared in the chat box.